This video is to help you get ready for the force board lab that you will be given soon. The first step is to make sure that the spring scales, there should be 3 of them, and that they are calibrated. If you get this kind of spring scale, there's a tab at the top that you will push up or down, and make sure that that tab is set to 0 when there's no force on the hook. If there's a force on the hook, then it shouldn't be set to 0. If there's no force on the hook, this is what you should see. Again, how do you adjust this? With the tab, like so. So this spring scale is calibrated because the tab is set at 0. If I pull it, I can register the force with which I'm pulling on the hook. Now you have 3 of these, and they are connected. They will be all 3 of them be connected to a ring, like that. In some configuration, different tables will have different configurations. The next thing that you do is you slip a piece of legal size paper underneath the spring scales. Like this, so that it's more or less, that the ring is more or less centered on the paper. Take a pencil, and you're going to make 1 dot. The first dot will be at the center of the ring, very center of the ring. Then you'll make 3 other dots, each of them in the direction that the spring scale is pulling. So after that, and then you record the measurements. So for example, this spring scale says 2.1 newtons. This spring scale reads 3.1 newtons. This spring scale reads 2.7 newtons. Once you do that, then you can remove your sheet of paper. So this is what you should expect to see after you take your data. The directions of each of the 3 forces, the center dot, and the magnitudes of each of the 3 forces. So then, now you need to choose a scale. Well, we need to choose a scale that will give you a reasonably sized diagram. The scale we're going to choose for this is that 1 Newton is 5 centimeters. Right? We'll try it. So, the scale is 1 Newton is 5 centimeters. So, if your force reads 2.1 newtons, how long does your force vector need to be drawn? 10.5 centimeters. So we measure off 10.5 centimeters and draw the force vector. 10.5 centimeters. So I'm starting from 11, which means I go to half a centimeter here. There's my first vector. Let's call this F1. So F1, force 1, has a length of 10.5 centimeters. I draw the arrow in the direction indicated by the dot. You could very well go through the dot, right? That just tells you the direction. You don't stop it necessarily at the dot. You draw according to the scale that you have chosen. 1 Newton is 5 centimeters. 2.1 newtons means 10.5 centimeters. Second force is 2.7 newtons. And that is 13.5 centimeters. So again, I'm going to do that. Line it up at 14 and draw to half a centimeter, which is there. Again, draw the arrow at the end of the vector. That's my second force. Am I going too fast? Is this all right? No. Okay. F2. So again, that's 2.7 newtons. Given that scale, is 13.5 centimeters. Finally, my third force, 3.1 newtons. 3.1 times 5 is 15.5, so 15.5 centimeters. So if I say 10 here, 15.5 is 25.5. Start there, and then I'm going to end there. Right. So that's my third force. And again, I've chosen each force has a magnitude and a direction, given my particular scale. Now, the ring is at equilibrium, which means that the sum of the forces is equal to 0. And so what that means is that F1 plus F2 plus F3 have to add up to 0, so the forces have to balance. So the next step is to add say, force 1 and force 2 vectorially, as in and graphically, to see what the resultant of adding F1 and F2 is going to be. Now, the next step in that is to measure the angle between F1 and F2. I usually do that with a protractor. The angle between F1 and F2 is 99 degrees. So this angle is 99 degrees. And since we're making a parallelogram to add these two vectors, if one of the interior angles is 99 degrees, the other interior angle has to be 81 degrees. And if you're making a parallelogram, this side was 13.5 centimeters. This side is 10.5 centimeters. So to finish the parallelogram, I need an 81 degree angle, which is in this direction, using the protractor. Right, 80 plus 1, 81. So it's in that direction. I made a little dot there to show me what direction I had to choose. And since it's a parallelogram, opposite sides have to be congruent, which makes that 13.5 centimeters. So I draw my 13.5 centimeter side through. Again, from the tip of this vector, I add my second vector. See, the 13.5 gets me from 22 to 8.5 centimeters, which is there. And then I finish the parallelogram by connecting the two other sides, like so, to finish the parallelogram. Now the resultant of adding F1 plus F2 is the diagonal from the center dot to the opposite vertex, like this. So I draw this. This is my resultant from the center dot to the opposite vertex of the parallelogram. That's my resultant. Let's call that F-res. Now we measure this. We measure it, and we get a length of 16 centimeters, 16.0 centimeters. So 16.0 centimeters. And if I go back and look at my scale, I convert my scale, I use the 1 Newton as 5 centimeters. That tells me that the F resultant force is 3.2 newtons. That concludes the drawing of a part of the show. Now, what we have to do now is compare the resultant force. Now, F3 is in this case called the equilibrant force. F3 is the equilibrant. It's called the equilibrant because it brings the system into equilibrium. You added F1 plus F2 to get your resultant force. The equilibrant should cancel, balance against the resultant force. So now your job now is to compare the resultant force with the equilibrant. There's two ways to do this. First, you compare the magnitudes. You find the percent error. Percent error for the magnitudes is the difference, the absolute value, right? So it's absolute value F-res minus F-equilibrant. Absolute value over what you expected. Well, you expected the equilibrant, so you compare that to the F-equilibrant, and then you multiply by 100 to get from fractional difference to percent difference. And you expect that the angle between them should be 180 degrees. So your percent error For the angle, your expectation is 180 degrees. Now we measure it. Again, measure so that it's less, that your difference is less than 180 degrees. And we measure it, again, lining up the vertex with the center of the protractor. And I got 171 degrees for my angle. So my angle measurement, 171 degrees between the resultant and the equilibrant. It's this angle between the resultant and the equilibrant that has to be measured. How do you find the percent error? Again, you take the absolute value of the difference over the expectation, which is 180 degrees, and then you multiply by 100. The smaller the error, obviously, the better your results. And I'm pretty sure this concludes our video. Thank you for listening.